Now that we know something about magnetic fields, we need to think about the force that particles experience when they're moving and they're charged in a magnetic field. So we're going to start a little bit with the basic conceptual idea, since that's really going to be the most challenging rather than plugging numbers into an equation. So the first thing to understand is that force is perpendicular. And when I say that, the question should be, well, perpendicular to what? Perpendicular to both our velocity vector and our magnetic field vector. And remember that you can have magnetic field varying through all of space. So what matters is it is the magnetic field vector at the point that the particle is actually at. So what that means is that the velocity vector and the magnetic field vector form a plane, and that the force is perpendicular to the plane. Now, any two vectors can always form a plane, so there isn't anything really special about this. So the only way that force can be perpendicular to both of them is if you imagine it being perpendicular to the plane that both of these face. Now, what we're going to actually get to here is the idea of a cross product using the right-hand rule. So that's why the angle in between these two vectors matters. So in general, there's some angle alpha. We typically use alpha, not theta for this. And our force vector is going to depend on what alpha is. As that angle gets bigger and bigger, you have a larger and larger force vector. So when velocity is perpendicular to magnetic field, you have the greatest force vector. Now, again, in all of these cases, they actually point in the same direction, right? So this is one thing to notice, is that your force vector can point in the same direction, and in this case, it's because we're just changing the angle of velocity with respect to b. So please keep in mind that this angle matters. In many situations, we're going to have the velocity vector being perpendicular to the magnetic field vector, so this is common. And it's really just common for us because it's simplest, right? So this is going to be the easiest to calculate, but it doesn't necessarily mean it's the only thing that can happen. So most of the problems you're going to see are going to be in this situation, but please remember that you don't have to be in this situation. So there are some situations where the force on the charged particle is zero, and this is pretty important to know because you should recognize these situations and not even try to do the calculation, not even try to use the right-hand rule. So there are actually three situations. Two of them are shown here. So the first situation is that the velocity is zero. So if you have a charged particle that is sitting still in a magnetic field, it doesn't experience a force due to the magnetic field. So this is pretty important. The only time that you have forces on charged particles due to magnetic fields is if they are moving. So we're usually going to not say that explicitly. I'll just say like, oh, what's the force on this charged particle? But it always must be a moving charged particle. The second situation is that these two vectors are parallel. This is the situation where alpha, our angle between them, equals zero. And as we frequently have with a cross product, the cross product of two vectors that are parallel to each other is in fact zero. And in this case, you could have the velocity vectors and magnetic field vectors parallel or anti-parallel, and in both cases your force will be zero. So it can be moving, but if it's moving in the direction of the magnetic field, your force is zero. The third case is if it's not actually charged, if Q is equal to zero. So please keep that in mind, that if you have a neutral particle, there won't be a force on it, that it actually needs to be a charged particle. So the other thing to keep in mind is that all of these pictures have actually been for positive particles. And just like with electric fields, if you have a negative charged particle, it actually is going to experience the opposite force. So now we have the actual equation. The force on Q, where that just means on a charged particle, and here we are assuming that this is a point charge, is equal to Q V cross B. So V is your velocity vector of that particle, B is the magnetic field vector at the location the particle is at. Now note that Q is multiplied in here, so this could be negative, which is going to flip the direction of this. right? So v cross b is a vector itself, but if you put a minus sign out front, you get the opposite direction. So to get the direction, you use the right-hand rule. Now, I don't actually like this right-hand rule the best. I'll make a separate video where I try to show me doing the right-hand rule of these things. But so notice that one way of doing it is V on the thumb, B on your second finger, and then F, the force, on your third finger. Now this would be if Q is positive, right? So V cross B gives you this. So if you had, for instance, an electron, you would need to be pointing down rather than up. So that's one way to do this right-hand rule. So if you just want the magnitude, you can say QVB and then sine of alpha, where alpha is the angle between V and B. Note that here it does look like V and B are perpendicular. That doesn't necessarily have to be the case. So for instance, if V was actually off this way, where it's still in the same plane, and I'm bad at drawing, then your thumb, like if this is my thumb, can point that way rather than here, and your middle finger is still up at that point. So do note that the angle between these actually does factor into the magnitude of the force, but it doesn't necessarily factor into the direction. I want to run through a few quick graphical examples. One of the reasons for this is that we have to represent this fundamentally in 3 dimensions. So whatever we do, we are trying to represent 3 vectors, which all are perpendicular to one another, at least a little bit, in a 2D plane. So the first situation, the force is 0. Why is the force 0? Well, the velocity vector is parallel to your magnetic field vector. So that's why force is 0 here. In the second situation, we see that our velocity and our magnetic field vectors are perpendicular to one another. And if you do V cross B with your right-hand rule, depending on how comfortable you are with that, your third finger would actually be pointing into the page. So how do you represent that? Well, one way of doing that is to literally write it F is pointing into the page. There's not really a different way to label that. So sometimes you're just going to have to write stuff down. Don't necessarily try to draw this in 3 dimensions. Some of you are very good artists, but in general that will just look terrible. So other things that will happen is that you might actually show the magnetic field or the velocity going in or out of the page. Remember that when there's X's, that means it's going into the page. So now we have magnetic field into the page, velocity vector to the right. So when you do V cross B, your force is up. So again, into the page and up are different directions. If you're looking down at your phone, this all might get very confusing, but up always means up with respect to the page. So now notice that the only difference between this third and the fourth picture is the sign of our charge. So once we go from a positive charge to a negative charge, the force points in the opposite direction. So one scenario that isn't shown here would be, for instance, the velocity going into the page or out of the page. You can just use this technique of writing that very clearly to the side or below it to try to make it clear what's happening.